Good morning and welcome to everyone today. I hope you had a nice evening yesterday and you have been able to process all the information. So we have a second day of this webinar, Dietary Biomarkers for Measuring Food Habits, Possibilities and Challenges, organized together with the Network in Epidemiology and Nutrition, NEON, and the Royal Swedish Academy of Sciences and EpiHealth. And we have a half day here. I'll show the schedule that we have. So we have presentations until and 2 breaks here as a start. And at 11:15, there will be a panel discussion. And after that, you will be able to pick up a quick lunch if you'd like, or you could just save it for after. Then we would like, if you want to join in some lunch discussions in breakout rooms, and we will provide more information about that when it's time. But that's the overview. First we have presentations, and then we have panel discussion, and then some group discussions. And that's the half day we have today. Remember to give your questions in the Q&A feature at the bottom, and we will try to answer as many as possible, depending on time. It can be tricky to answer all, but ask them there, and we'll try to give them to the correct speaker. Yeah, I guess that's the information you need at the moment. We'll move on to the first speaker of today. And to him, I will not say good morning. I will probably say good night. Phil Choi is here from Australia, flew all the way in. And he has his PhD and postdoc from University of Queensland, Australia, and now he works at Queensland Health. He will probably present himself, I hope. So I'll give the word to Phil. Welcome.
Thank you. I'll just start sharing. All right, thanks for that, Stina. I'm Phil. I'm not a real researcher anymore, at least. But today I'd like to talk about wastewater-based epidemiology, and in particular, how food biomarkers have a role in this space. And overall, what I really want to do is challenge your thinking of what a food biomarker actually means at the population level. All right, so as you know, our urine and our feces contain lots of different biomarkers that reflect what we eat and how we live. And this is the kind of information that people like yourselves will be working very hard to sample from and to study. Yet we know that every day, people in the general public are flushing all of these urine samples and feces samples straight down the wastewater, straight down the toilet. What a waste. But thankfully, there is a way to make use of this information. And that's called wastewater-based epidemiology. So in wastewater-based epidemiology, well, it relies on people going to the toilets, doing their business and flushing it down the sewer system. This then combines with waste from other people's houses, other buildings, offices, industries, and so forth. And in developed communities, this gets sent to a wastewater treatment plant. And by sampling wastewater at the inlet or at the entrance of the wastewater treatment plant before it gets processed, we have what is basically a form of population pooled urine and feces sample. And this can contain contributions from thousands or millions of people, depending on how big each wastewater catchment is. And we can try to measure things in wastewater and express our results in terms of the mass of a biomarker excreted by a community. We can also find the population of different catchments and then express our results in terms of the mass of a biomarker excreted per capita or per person. For certain biomarkers, such as drugs that have pharmacokinetic information, we can also express this in terms of doses consumed per capita. So this is how wastewater-based epidemiology works. It's akin to a pooled population urinalysis study. And this sort of methodology has been in use for for about 15 years now. And it's been used primarily to measure drug and pollutant levels. So here, for example, we're looking at cocaine biomarker levels in the wastewater in a community in Australia over time. You can see that the population loads of these biomarkers are lowest during weekdays, shown in blue, and higher during weekends, shown in red. And you can see that there are lots of peaks during special events. These are all basically public holidays. So this shows how wastewater-based epidemiology can be used in a powerful way to give us information about consumption habits in the general public, and in a way that you couldn't get from other means, such as through surveys or through individual urine analysis. That would be very difficult to do. So this is the kind of thing that wastewater is really good for doing. In more recent times, and this is what I spend a lot of my current work doing, is wastewater is also being used to measure COVID-19 in communities. So COVID gets excreted in people's feces, and we can measure that in wastewater. So this is an example of results from a community in the United States, where they have the normalized levels of COVID virus in from the wastewater, shown in blue. And it's being compared to the number of clinically confirmed cases, shown in black and gray. And you can see that in certain cases, wastewater actually gave you a prediction of the COVID-19 cases in the community. And that's because wastewater analysis doesn't rely on people coming forward to give samples. It doesn't rely on having hospitals, doesn't rely on more regimented testing, etc. One of the companies that do this sort of testing services in the United States actually also gives, I guess, predictions of the COVID incidents that you should expect in your community, given the wastewater results. So it's a kind of forecasting, if you will. And what I want to stress here is that wastewater is useful because it provides information on the health of the general public. So not just people who turn up to provide samples. I've suggested that wastewater-based epidemiology is similar to urinalysis, but there are some important differences. For example, because we're measuring entire populations, we can't distinguish between variations between individuals or contributions from different individuals. So everything is at a population level. That also might be some people might see that as a drawback, but it also means that individual privacy is respected because the results literally get mixed in with everyone else's. Also, compared to typical urinalysis, there are fewer limits to how often you can take a sample or when you can take a sample. So you can take samples every day if you wanted to, all for a relatively cheaper price than typical urinalysis studies. So in Stockholm, for example, I'm told that you can cover most of suburban Stockholm from 2 samples and 2 wastewater treatment plants. So this is what wastewater-based epidemiology is. And as I mentioned, it's being used primarily for drug, pollutant, and more recently COVID related things. Several years ago, when I started at the University of Queensland, we asked the question, can we use wastewater-based epidemiology to find what foods people are consuming? To answer this question, we had to first understand what makes a good wastewater-based epidemiology biomarker. A good biomarker for wastewater purposes needs to meet a number of criteria. For example, it should only end up in the sewer through human urine or feces. So this means that things like small sugars and some small alcohols are no good because they can also end up in the sewers as a result of kitchen waste or industrial waste, waste from restaurants and so forth. But good biomarkers should also be specific to certain foods, different food groups or different diets and nutrients. And that's because we want to reduce uncertainty in how we interpret the results. So this means things like urinary nitrogen, creatinine, etc., are not good as indicators of meat consumption because you can excrete them after not eating meat, for example, after taking performance-enhancing supplements and so forth. Another factor, which I'll get into later, is that they should ideally be stable in sewers. So this meant that this really cut down the number of biomarkers that we could consider. So the potentially good-looking biomarkers were some of the alkyl-resveratrol metabolites or the vitamin B catabolites, especially because these things are not present in significant quantities in the original food, and we know why you would be excreting these products. And things like proline butane as well. So the way we went about answering this question, we did a literature review to find all sorts of potential food or diet or nutrition biomarkers. And for the ones that we could buy analytical standards for, I set up a mostly typical reverse phase LC-MS method to measure these in wastewater. And then we conducted stability studies to see how these biomarkers behave in sewers. And this is important because what you put into a sewer is at one end is not necessarily the same as what you get out. Biomarkers can degrade because this wastewater is full of microbial life, which threaten to degrade biomarkers. And if a biomarker degrades significantly during its time that it gets transported in the sewer, it means we can't use it quantitatively because we're not very confident in the levels of the biomarkers and how it gets transported. So in order to understand the stability of a biomarker, we dosed biomarkers into these things called sewer reactors. These are basically containers full of wastewater and sewer biofilm, so microbes basically. And we use them to understand degradation under specific and controlled conditions. It's kind of like using hepatocyte assays to understand biomarker transformation. And the results from these experiments basically told us that pretty much all the food biomarkers degraded in most sewer conditions. Well, it's a bit complicated to get into detail. Each of these charts for each biomarker shows the stability profile under different key sewer conditions, shown in different colors. And you can see that things like 2-PY and enterodiol degraded in one of the key conditions, whereas the meat biomarkers, pretty much all the meat biomarkers degraded in all of the key sewer conditions, which meant there is extra uncertainty when we measure these. The amount that we measure at the wastewater treatment plant is not likely to be the amount that actually gets flushed down the toilets. So this really cut down the number of biomarkers we were confident enough to use going forward. At the same time, we also took wastewater samples from about 40 different sites and points in time in Australia and tried to measure these diet biomarkers, as well as some other biomarkers, which I won't talk about here. And this chart here shows the distribution of each biomarker in the different samples, with the average for each indicated in red. And this is expressed in, again, loads per 24-hour per person. And if you look closely, you might notice that the variation in the distribution of some of these biomarkers vary quite a bit. So for enterolactone, there was about 1 order of magnitude of variation, whereas for other things like hippuric acid or TMAO, we saw 2, almost 3 orders of magnitude of variation. And this immediately tells us that there was some noise in the data, potentially as a result of degradation, for example. We also compared these per capita loads to loads reported in urinalysis studies to identify the biomarkers whose wastewater loads agreed with what the literature was saying. And in doing so, we eventually identified or settled on 7 biomarkers, which are shown here in bold. And these biomarkers were ones that didn't degrade too quickly in the sewers and whose measurements agreed with previous literature. In other words, these were biomarkers that we had reasonable confidence that there is not much uncertainty in measuring these from wastewater. These other biomarkers did not meet this sort of criteria. At the same time, we were also conducting another study, and this study is a bit special because we were taking wastewater samples, as we usually do, but we were taking wastewater samples at the time of the national census in Australia. So we got samples from about 20% a bit over 20% of the Australian population. And for each wastewater catchment, or for each community that we took samples from, we also got metadata, if you will. And this was social, economic, and demographic metadata. So things like age, socioeconomic status, whether you have multiple cars, whether you have certain occupation classes, and so forth. And what we did was, with the wastewater samples, about 140 maybe, we measured a panel of biomarkers, mostly pharmaceuticals, but also some of the diet biomarkers that we deemed to be, that we had higher confidence in. And we looked for relationships between these two data sets. In other words, we had patient data, where the patient is a community, and we had patient metadata, and we tried to look for relationships. And I'm going to plot the results for each biomarker on this plot here. So this is simply a plot of correlation coefficients. So negative correlation coefficient with age in this instance, positive correlation with age, correlation with socioeconomic status, so positive and negative. What we found was that most of the diet-related biomarkers were significantly correlated with socioeconomic status. So the fiber biomarker, the mammalian lignans, the vitamin B3 biomarkers, proline betaine were all significantly associated with higher socioeconomic status. In other words, you tended to see more of these in the community when people were richer. We didn't see quite any significant association for alpha CEHD, which is a vitamin E biomarker, and some of the artificial sweeteners, for example. And you can see the things that correlated with older age and poorer, lower socioeconomic status for mostly opioids, antidepressants, and so forth. Now, we can also try to look into more specific descriptors, not just age and socioeconomic status. So if you look at this plot and just focus on the things that are shown in blue, this is a plot of the load of different biomarkers plotted against the proportion, the percentage of the population that pays high rent. So this would be, I think, about 300 or 350 euros per week in rent. So when you had more people in your population paying high rent, you tended to have higher levels of 2-PY, the vitamin B3 catabolites. Inversely, if you look at the things that are in black, when you tended to have more people in the community who were under the age of 70 and had a disability, you tended to see slightly lower numbers of lower loads of 2-PY. And this overall suggests that there seems to be a rent and disability or medical health outcome related component to the consumption of vitamin B3 in Australia. We can also look at some of the other biomarkers. So for enterodiol, for example, we found that you tended to have lower loads of enterodiol when you had fewer people in your catchment who were employed as managers. And you tended to have lower levels of enterodiol when you had more people in your catchment who didn't finish year 12. And this suggests that there's an educational or manager-related and occupational component to the consumption of fiber in the communities, and which suggests that if you're interested in interventions around trying to make people eat more fiber, for example, you could try to look at an educational-driven intervention or an occupational one as well. For ethyl sulfate, an alcohol biomarker, which we have lots of experience in analyzing, we found that it was higher in places that paid lots of rent and lower in places where people had a low occupational skill. Now, the relationships between these biomarkers and these socioeconomic indicators was so strong that we were actually able to predict socioeconomic parameters of communities based on the different loads of biomarkers that we measured. And we published this as a study. And the main thing that I want to highlight here is that the diet-related biomarkers or the food-related biomarkers had very high loadings in this PLS model. So the main messages that I want to convey today is that wastewater is a bit like urine analysis with important differences, such as you have to take into consideration degradation, and there are differences in the way that you can interpret the results. Nevertheless, we can measure some diet biomarkers or food biomarkers in wastewater in a qualitative way. There's potential to use this sort of wastewater approach to understand how public health interventions go forward. I didn't talk about it in today's talk, but there's more progress in being able to use proteomics in wastewater. It's been a slow progress because wastewater is such a complex matrix. And also metagenomics as well. There are studies that suggest that you could measure different microbes in the wastewater to tell you how much of your population is vegetarian compared to how much of your population eats a lot of meat, for example. And of course, there'll be benefits from using non-targeted mass spectrometry methods to measure biomarkers in wastewater. And lastly, the real key message that I want to deliver here is that I think in coming years, we'll see wastewater play an increasingly important role in our understanding of population behavior, population health, and the exposure zone in general. So thanks for listening to me today. I'll also leave you with a list of some of the biomarkers that I tried for this project, but which failed for one reason or another. Thank you.
Thank you so much, Phil. Super, super interesting. I just wanted to, we have some questions in the chat, but I just wanted to ask one question first. So I assume that like what you lack in individual data, you gain from having data available all the time. You can measure every day. If you do that in individuals, you have to invite them all the time, and that's not feasible. So I was wondering, does these samples, are they saved and stored? Do you have a biobank of samples, and can you, or is that something that?
Yes, in Australia at least, we have wastewater samples for some sites going daily wastewater samples from as far back as 2011 or 2010. In addition to our normal censuses, there's a research group at the University of Queensland that does a census of wastewater in Australia. And of course, all these samples are stored.
Cool. So you can go back to like, yeah, June 2012 when this event happened. We can go back.
Yes. In fact, there are a number of relatively high profile studies showing that they found COVID in the wastewater in December 2019 outside of China. Those are a bit controversial, but it's not the first time wastewater has shown that there have been things present in the wastewater long before they turned up in hospitals.
Yeah, interesting. Okay, so in the Q&A we have, I'll start with this question. Regarding wastewater epidemiology for assessing drugs or COVID in a population and not in sole individuals, how does the ethical process work?
That's a good question. For things like drugs and COVID-19, the consensus is that the benefit that we get from understanding these often very important aspects of population health vastly outweigh any potential privacy concerns. And the fact is, unless you're taking wastewater from a community that serves 100 people, which basically doesn't happen in most countries, there are no ethical concerns that an individual should be concerned about, because at the end of the day, you're just measuring some chemical or a biological entity in a sample, and there's no way, and it doesn't come with a name tag. So we can't say John did it or Susan did it yet.
No, exactly. And then we have another question. Let's see. When comparing two different sampling sites for wastewater biomarker, do you have problem with normalization per capita? I guess the dilution of the samples would differ depending on the facilities connected to the system.
Yes, that's a good question. The short answer is it doesn't matter. So wastewater treatment plants always measure the volume of wastewater that comes in. So even if it's a rainy day and the water is diluted, we'll know exactly how much it is diluted by. The main thing that gets in the trouble of normalizing is when you measure biomarkers that degrade a lot. And that's because the sewer characteristics can vary from one place to another. But for most biomarkers that are used for wastewater-based epidemiology, this is not a major concern.
Okay, that's good. Great. I think we have to move on. It's time. Thank you so much, Phil. Really great. We will move on to Lorraine Brennan. She's a professor at the Institute of Food and Health at University College Dublin, Ireland. And yeah, I'll give the word to you.
Good morning. Can you see my slides okay?
No, not
yet. Okay. Okay, I'll try that again. Can you see that now?
Yes, that's
okay, perfect.
Thank
Good morning. Thank you very much for inviting me here today. I'm delighted to be part of this workshop. So I'm going to talk about metabolomics-based dietary biomarkers, current status and future opportunities, but I'm going to go very quickly through my introduction because we've heard a lot about dietary biomarkers yesterday and indeed this morning. So what I hope to do this morning is really focus predominantly on the use of biomarkers and how we can potentially use them in the context of nutrition research. And then I'd like to spend a little bit of time talking about key conclusions and some of the challenges that we face, because it is a very difficult area to work in. So if I move quickly then on, I don't need to introduce food intake biomarkers. We're all here because we have a very big interest in them. And we know that we have an interest in them because we're really hoping that they can help us overcome one of the major issues we have in nutrition research, and that is the limitations associated with self-reported intake. So we've heard about these already yesterday. So we know that we have issues with estimating portion sizes. We know we have issues with people over-reporting foods that they perceive to be healthy and under-reporting foods that they perceive to be unhealthy. And biomarkers can offer the potential of being objective measures of intake, so helping us overcome some of these measurement errors and errors that are associated with self-reported data. However, I think that we need to be very careful because I don't think biomarkers will completely replace self-reported data. Self-reported data will still be very important, and it will be important for capturing foods that we just can't get good biomarkers for, or for capturing other aspects of our diet which are very important in the context of health and disease. So what I'm going to talk today about is very quickly about approaches that we and others have used about how to find biomarkers of food intake. And then I'm going to move very rapidly into trying to show you how we can apply them and some of the challenges that we face when we do that. So us and others have used control intervention studies where we feed volunteers exact quantities of food and we look for changes in biomarkers following the controlled interventions, and these have the potential of being objective measures of intake. We then follow this up with dose response studies looking to see if we increase the portion of food, can we increase the concentration of the biomarkers. And then finally, it's really important that we look at the termination of intake in independent studies, because up here in these two scenarios, they're very controlled environments, and we do need to see, do our biomarkers hold up in independent studies? So I'm going to take you very quickly through one example of how we've done this for a particular food. And I'm going to focus in this example on legume intake and how we went about identifying biomarkers of legume intake and how we done some part of the validation of the biomarkers. So this work was done as part of the foodball project. We were particularly interested in legumes and we used peas as the example. We performed an acute intervention study, collected urine samples, performed mass spec analysis on those, performed our usual statistical analysis, and came up with a list of biomarkers that looked like they were changing following consumption of the peas. And examples of the kinetic profiles of these biomarkers are shown here. So you can see that these biomarkers are increasing following consumption of the peas, and in following consumption of our control food, they remain relatively stable or unchanged. We did find biomarkers that were changing in response to both foods, and these, of course, are not particularly interested in these in terms of biomarkers of intake of peas. So we were able to narrow down our list of potential biomarkers. And then once we'd done that, then we had to confirm the identification of them. So performing LC-MS to identify them, and then to try get standards to confirm the identification of these biomarkers. So once we'd done that, then we went on to perform a dose response study where we had individuals consume randomly different quantities of peas over 3 weeks, and we collected biological samples at the end of these weeks. And you can see over here, this is an example of one particular biomarker, and you can see that as the quantity of P increases, so too does the urinary concentration of this particular biomarker. So this was very exciting. We had identified a biomarker in an acute study, then taken it into a dose response study and shown that it had a dose response to it. And then to bring it into a different context, we were very lucky that our partners in Copenhagen in this particular project had used peas as a control study, as a control food in one of their studies. So we were able to go into their samples and look for our biomarkers, and indeed show that in their population group that this particular marker also responded to pea intake. So a very nice confirmation of the biomarker in an independent study. So that's just very quickly to show you the concepts behind how people identify biomarkers and how they go on then to validate them. And there have been many, many examples of this in the literature. And you can see I've just pulled up some examples of different foods. And it's very exciting because every couple of months, we're getting more and more of these papers emerging that have identified potential biomarkers for foods. And there are also a series of systematic reviews published as part of the foodball project that really went through the literature systematically, looking at a range of different foods for biomarkers. So I think the field is very exciting. It really looks like we're starting to emerge, to have emerging a lot of biomarkers that are associated with different foods. But my question for today is then, how are we going to use these biomarkers? How can we make a shift forward in their use? Rather than just identifying them, how are we actually going to potentially use them in the context of nutrition research? So if we stand back and we look at how we could potentially use them, we can broadly divide it into four areas. And the first would be to measure adherence to dietary intervention. And this would be really important as the concept of precision nutrition emerges. We're going to really be questioned about, can we really show that we have individuals adhering to dietary intervention? And biomarkers have a huge potential in this role, really showing us and demonstrating that individuals are adhering to the interventions we're performing. So a very exciting area here. In the context of being objective measures of dietary intake, that's what we all would like. So again, a very exciting field as the more and more biomarkers emerge in the literature. And an area that we're particularly interested in is to try and use these biomarkers in combination with our self-reported data. And can we use the biomarkers to correct the self-reported data? And then finally, we heard some of this type of work yesterday, where you can use biomarkers to look at the relationship with food intake and health and disease parameters. So an area again that's growing, and it's very exciting. So then to start with this objective measures of intake. So can we really get an objective measure of intake from our biomarkers? So I'm going to give you an example from some of our own work where we did that. And I should say upfront that I don't think that all biomarkers will be able to give us quantitative measures of intake, but that doesn't mean that they won't be useful in some other ways. So the idea here, or the concept we all would like, is that we take a biological sample, we determine a biomarker concentration, and from that biomarker concentration, we're able to get or determine the food intake in terms of grams per day. So we tried to test this out with a biomarker that was well known in the literature and well established as a biomarker, and that was the biomarker proline betaine for citrus intake. And to help us move this forward, we performed a very controlled intervention study where we had individuals consume exact amounts of citrus, and we measured then the proline betaine in the urine samples. And the concept behind that then was that you could take a proline betaine in any urine sample and then use the equations that we obtained from this controlled intervention to determine the citrus intake in that particular sample. So just before you develop a new method, or you try to develop to move forward a new method, it is very important to compare it to what we currently use, or our gold standard. And our gold standard for estimating intake is self-reported data. So for us, it was always very important to look at the relationship with anything we've done with biomarkers with the self-reported data. So the concept here is that you take your biomarker data, you have your control feeding study curves, you plug your biomarker data into those curves, and you estimate your intake. And that's solely estimated on biomarker data. But then we wanted to compare it to our habitual intake that we would have obtained from 4-day semi-weighed food diaries. So to do this, we went to our National Consumption Survey in Ireland, which is called NANS, so the National Adult Nutrition Survey. And this had data from approximately 600 individuals where we had food diary data, so semi-weighed 4-day food diary. We estimated citrus intake from this, and we called this reported citrus intake. We then had urine samples from these individuals. We measured the proline betaine levels in these urine samples, and we were able to plug them into our equations that we obtained from our controlled intervention study to estimate or to predict citrus intake using the biomarker data. So we wanted to compare to see how well our predicted intake agreed with our self-reported data. But before we done this, we wanted to see, well, is there a way we could test a model within the controlled intervention study to see, well, does it work? Is it going to work? So our controlled intervention study was done on 50 individuals. So we were able to take 2/3 of that data to develop the calibration curve and leave out 1/3 of the data. And by leaving out 1/3 of the data, we were able to check to see, well, how, if we took this 1/3 of the data, how well could the predicted intake agree with the actual intake of those individuals. So that's what we did. We estimated our predicted intake from these individuals based on the urine data and compared it with the actual intake that we knew from the intervention study. And you can see that here, this is the actual actual intake of orange juice in this case. And here is what we predicted from the urine samples. So you can see over a range of different intakes, there was very good agreement between the actual intake and the predicted intake. And what was very interesting about this is that if we looked at the correlation coefficient between either fasting urine samples, this is first void morning fasting samples, or 24-hour urine samples, we got, for both cases, we got extremely high correlation curves, our correlation coefficients. And the correlation coefficients are high in this instance because it is actual orange juice intake that we have for these individuals. So then if we go back to our original question was, well, how well does it compare to self-reported data? Again, we took our proline betaine in our National Adult Nutrition Consumption Survey, plugged it into our curves and estimated citrus intake from the biomarker data. And again, if I take a snapshot of the data, here is the recorded citrus intake from the semi-weighed 4-day food diary, and here is the predicted citrus intake from the urine sample. And you can see again, across a range of intakes, we have very good agreement between the two sets of data. And if we look at this over the 600 individuals in this instance, you can see that on the whole, we have very good agreement with a very low mean bias here. However, we do have individuals where there is very poor agreement, and we would expect this. And in these individuals, what's happening is when we're getting underreporting of their citrus intake, and the biomarker level is giving us much higher levels of intake. But on the whole, extremely good agreement between what we can estimate from urine samples, what the individuals actually ate in the intervention study, and the self-reported data in the semi-weighed food diaries. So a very nice example of, yes, we can do this work with objective biomarkers of intake. So if we move on then and we look to see then if we want to work in large studies and moving into the realm of large epidemiological studies, a question we asked, well, do we need to have biomarkers for all samples? And is there a way we could combine the biomarker data with the self-reported data? And the concept behind this is that you have biomarker data and self-reported data for a certain portion of the population, and you model the relationship between these two in the context of calibration equations. And then you take these estimates from the calibration equation and you use these to calibrate or to correct the self-reported data in your larger sample size. So again, we tested out this concept using proline betaine as an example of a biomarker of citrus intake. And you can see here, these are the calibration equations that we used. So you have your biomarker derived estimates of intake, you have your self-reported estimates of intake, and you model the relationships between these, and you can calibrate then the mean daily intake of citrus using these estimates. So we carried out this on the National Adult Nutrition Survey, and you can see that here is your self-reported data, and then you have your predicted data in grey. So it worked very well for us, and we have developed an R package to do this, and also a Shiny app that's available that you can do this type of modelling in. So a key question then that arises, well, you can actually use this concept, but then how much biomarker data do you need to develop good, stable calibration equations? So we used simulation scenarios to try simulate different scenarios to see, well, how much do you actually need? And what we found was that you get a rapid stabilization of the standard deviations of the estimations when you have around 20 to 30% of the population. That is, when you have biomarker data for about 20 to 30% of the population. So we would be happy to say that when you have, in this particular instance and in the simulation scenarios that we use, that you needed around biomarker data for about 20 to 30% of the population to estimate those calibration equations, and then that you could use those estimates then going forward to correct the self-reported data. So just to reiterate what the concept here is that you have your biomarkers, you have self-reported data, you develop calibration equations in the relationship between these two, and you use those calibration equations then to calibrate or correct self-reported data in larger sample size. So we've done this for the example of citrus intake, and there are more examples that are emerging in the literature now where they've done it for other types of foods and, importantly, other types of nutrients as well. So then if we move on then and we think about biomarkers, but biomarkers, not all biomarkers that we identified that are food intake biomarkers are going to give us quantitative relationships with intake. However, they can still be very useful. And in this context, these biomarkers can be related to food intake. You could have multiple of them. They may not all give you quantitative information about the food intake, and they may be influenced by other types of parameters. However, they can be extremely useful when modeling then the relationship with health and parameters, disease risk factors, and disease outcome measures. And we're seeing more and more of these types of measures appearing in the literature. And this is also a very exciting field for biomarkers and very exciting applications of biomarkers. So for then the last part of my talk, I want to touch a bit on dietary patterns, because we're particularly interested in dietary patterns, and we know that we don't eat foods on their own, we eat foods in combinations, and there is an emerging literature that it's the dietary pattern that is particularly important. So a good few years ago now, we had the concept of trying to build a classification model where you could classify individuals based on their metabolomic profile into a dietary pattern. And we've done it very crudely using two very simple dietary patterns, a healthy dietary pattern and an unhealthy dietary pattern. So more recently, we've refined this model, and it's just in press at the moment, where we've taken biomarker data, we've built a new metabolomic based dietary pattern based model based on biomarker data, and to classify individuals into 4 different types of dietary patterns. So a moderately unhealthy, a convenience, a healthy dietary pattern, or a prudent dietary pattern. And what we'd done then was we went into an independent study, and we used the model that we developed up here to classify the individuals in this independent study into one of the 4 dietary patterns. And what was interesting about this independent study is that we had 4 time points. So we were able to track to see, was it reproducible over the 4 time points, and did individuals stay in the same dietary pattern over those 4 time points. So what we found was that the actual reproducibility was very high of the dietary patterns, and you can see that this is the moderately unhealthy dietary pattern, and you can see that each color is a different study visit, so it's a different time that we got biomarker data from these individuals, and you can see that there was very good agreement between the 4 time points in all dietary patterns. So this was just one example, and over here is another example. So again, this whole field of dietary patterns is starting to emerge. I think there's much more work to be done in not only refining the dietary patterns, but also in trying to make sure that they are reproducible across a number of different population groups and population targets. So then just to conclude, we've seen today and we've seen yesterday that food intake biomarkers are very exciting. Metabolomics is playing a huge role in the identification of these new food intake biomarkers. From the work that I've shown you today, I showed you that the biomarkers can perform well in determining intake compared to a 4-day food record, which is your gold standard for habitual intake. Biomarkers can have the potential of classifying individuals into dietary patterns, and they also have the potential for combining with self-reported data. And I think that this combining with self-reported data is a very exciting feature that will emerge further in the literature in coming years. However, all of this is very challenging, and I would just want to highlight some of the challenges that are associated with this. When you're working with metabolomic profiles, you have a huge number of unassigned features, and it can take a long time to identify the features. Many of the metabolites that we are interested in identifying are not present in your standard databases. So a huge amount of work is put into trying to identify these biomarkers. And this needs efforts and an international alignment to move this field forward. There is a lot of biomarkers emerging in the literature. However, we need to validate this. This work is often very difficult to do and requires further studies, and funding to do this and carry out this work can be difficult to obtain. Dietary patterns, again, is an area that has great potential for the role of biomarkers in identifying dietary patterns. And then a question that again needs to be identified is, well, how many repeated measures should we do in biological samples to get an estimate of habitual intake? And again, this is something that needs a little consideration and thought. And then finally, combining with dietary data is a very exciting area. So then just to wrap up, I've highlighted some of these already, but one thing that I haven't mentioned is that what's emerging from a lot of the work at the moment is that multiple biomarkers are associated with a particular food. And that means that panels of biomarkers are going to become more and more important. And with that, it brings in statistical challenges. We don't have the correct we need to develop new statistical tools that will allow us to correctly model these panels of biomarkers with one specific food. Again, we need new approaches for combining self-reported data with biomarker data. And again, we need more work in validating biomarkers and also in moving the dietary pattern field forward. So then, just to wrap up, I'd like to thank the team in Dublin for all their Trojan work in performing some of the work that I've highlighted here and other work. I'd like to thank our collaborators on numerous projects and of course our funders for supporting us, and thank you for listening.
Thank you, Lorraine. Really great. Very exciting to hear your thoughts on this. We have some questions. I'll start with this one. Would you need a much larger sample if you calibrate intakes that are more difficult to self-report compared to citrus intake? For example, more irregularly eaten foods, like fish.
So more irregularly eating foods. Yeah. Probably then at that instance, you'd have to do nearly a pilot just to see how well you can get your estimates of the calibration working before you know how many biomarkers you need to measure in the population group.
Yeah. And we are a bit short of time, but I think it's important that we take a few more questions actually. So one is, how can the calibration models handle non-compliant subjects? I suppose they cannot, question mark.
No, non-compliant subjects, no. So when you're modeling the relationship between the intake, so I guess they mean under-reporting in that instance, or over-reporting. So you're only going to have a certain proportion of them, and I think you can probably, one way of doing it would be that you at the beginning, from that estimating or modeling of those relationships, you remove your underreporters, and then you use your biomarker data to correct the self-reported data.
Yeah, and I have a question. You usually, or traditionally, you classify biomarkers maybe into recovery biomarkers, predictive biomarkers, and concentration biomarkers. Are those still valid classifications, and would you consider the proline beta-in as a predictive biomarker, as you could use it to predict intake? And how do you?
Yeah, so as part of the Foodball project, Lars spearheaded a completely new definition of biomarkers, which is much more flexible. So I think sometimes we get ourselves tied up in knots with a very rigid biomarker classification, where there's probably no need for us to be doing that, and having a much more flexible biomarker definition, I think it is more beneficial for us. I tend to move away from our classical approach of rigidly putting a biomarker into it, because I think it limits us.
Yeah, but I mean, I've been taught that to be able to use the biomarker for calibration purposes, it has to be recovery or predictive. You can't just be on a concentration level biomarker. So
there are papers emerging now that have shown that they can work with the concentration biomarkers. So, for example, if you look at from Ross Prentice's group in the US, he's just published some on concentration biomarkers, and they work. Yeah.
Yeah. Okay, so that's good to know that we can maybe start using calibration equations more than before. There are more questions. How sensitive are the urine samples to storage before analyzing for biomarkers?
So it depends on the biomarkers, and I think we saw that in the last talk as well. So some biomarkers will be very sensitive, and some biomarkers will be more stable. So stability will depend on the biomarker, but you need to be storing the biomarkers the urine samples at -80 would be the recommended, and get them into the -80 as quickly as possible.
Do you usually use some preservatives, or you don't?
We don't. We collect all urine samples under chilled conditions and keep them chilled throughout, and then get them frozen. Now, I do know others do use preservatives. We just don't, because we found it interfered a bit with our mass spec.
Great, thank you. Let's take one more question. Is there any way to get below needing biomarkers on 20 to 30% of your sample, as this may be difficult to achieve in large cohorts?
Yes, we were when we first published this, we were pushed quite a bit on this, because no matter what simulation study, that seemed to be, you got the best results with 20 to 30%. Now, you still got good results when you were lower than 10%, but we went very conservative, and because that was where you got your best results. You have to realize that if you go lower, you will get results, but you are bringing in other errors into your calculations. So you can go lower, but we would recommend in this instance that it was 20 to 30 for the best possible results.
Yeah, okay. So you can go lower if you have a really large...
Yeah. I think it was, in our example, you could have gone down to 10%, but you were bringing in other errors at that stage, yeah.
Great, thank you. Thank you so much, Lorraine, really good. I think I've already stretched the time here. So we will go on a break until 10:05. So I'll see you back then.
Welcome back from the break, everyone. And now it's time to present the next speaker. And that's Tim Interman from Leibniz Institute of Prevention Research and Epidemiology. And he's a postdoc there working, in Germany. And he will present his work on spot urine biomarkers and 24-hour diet recalls, validation and measurement error correction. So please, Tim, you can start.
Yeah, hello everybody, ladies and gentlemen. Thank you very much for the kind invitation to present our research on urine biomarkers for validation and measurement error correction of 24-hour dietary recall data in epidemiological study. First, let me give you a short introduction. Almost the entire dietary intake can be recorded with 24-hour dietary recalls, but 24-hour dietary records are assessed on a daily basis and self-report, so the data is subject to daily variation and measurement error. This leads to biased associations between dietary exposures and health outcomes. And if the measurement error is systematic or differential, these associations cannot be corrected using repeated measurements. Therefore, objective biomarkers are needed. They are not perfect, but they can reduce bias in associations analysis. Unfortunately, only few dietary biomarkers exist, and even less is known in children. Furthermore, statistical correction methods are not fully exploited. Therefore, our aim is to use different statistical methods to investigate two recently proposed objective urine biomarkers in children and adolescents. The first one is the sum of urinary sucrose and fructose, and the second one is the urinary sodium-potassium ratio. Since it's often not feasible in large epidemiological studies to assess 24-hour urine, we focus on biomarkers measured in morning urine only. The first one, the sum of urinary sucrose and fructose, was used for validation of 24-hour dietary recall reported sugar intake, and the urinary sodium-potassium ratio was used for correction of associations between dietary sodium-potassium ratio and blood pressure. What methods did we use for that? All our methods are based on study data from the EDIFIX family cohort, which was established to improve young people's health and to tackle the pandemic of obesity. In the baseline survey, more than 16,000 2 to 9-year-old children from 8 European countries were examined. The countries range from Cyprus in the south to Sweden in the north. We collected enormous amounts of data, for example, the BMI, the systolic blood pressure, information on education, on dietary behavior, which was measured using a 24-hour dietary recall and a food frequency questionnaire. Furthermore, biomarkers were measured in spot urine. In the baseline survey, in T0, the sodium-potassium ratio was measured in more than 12,000 children. And in a follow-up, the sum of sucrose and fructose was measured in more than 200 children and adolescents. So how did we exactly measure the dietary intake? We used two different 24-hour dietary recalls. The first one called Sakina and the second one Sakana. Both are proxy or self-reports of all consumed food items of the previous day for children and adolescents. Sakina was a computer-based version and Sakana a web-based version. The interviews were supported by photos, as you can see here, for the correct estimation of jam intake. Then the data was linked with food composition databases to derive sugar, sodium, and potassium intake. We repeated the 24-hour dietary recalls on several days, but in the end, we only assessed single days and not the usual intake, which we are normally interested in. How did we measure the urine biomarkers? The morning urine was collected at home and brought to the study center on the same day by the participants. The 24-hour dietary recall was provided on the same day. Then the urine analysis was conducted in a central laboratory where the sucrose and fructose concentrations were determined using an enzyme-based kit, and the sodium and the potassium concentration was determined using an iron-sensitive electrode method. The sum of urinary sucrose and fructose was expressed as milligrams per gram of creatinine to correct for fluctuations in urine volume, which was, of course, not necessary for the sodium-potassium ratio. After data assessment, how did we analyze the data statistically? The statistical analysis can be separated in two parts. The first part is the validation part, where we used correlation coefficients, the method of triads, and linear regression models. In the second part, we tried to correct the associations between the sodium-potassium ratio and a-specific Z-scores of systolic blood pressure. Therefore, this is a correction part of the analysis. There we use the so-called naive approach, the classical regression calibration approach, and the NCI method, which can be considered as the advanced regression calibration approach, which was specifically developed for correction of 24-hour dietary recall data. More specific, what were the underlying assumptions of the different methods? The correlation analysis did not need any further specific assumptions. Regarding the method of triad, there we needed a surge measurement for the sugar intake. There we used the frequency of food items with a high content of sugar, which was derived from the FFQ. Then we were able to calculate so-called validity coefficients for the 24-hour dietary recall reported sugar intake, which are often used as an approximation for the correlation between the true intake and a measurement of intake. The validity coefficients can be calculated using the formula, based on the correlation coefficients between the recall, the food frequency questionnaire, and the biomarker. The underlying assumptions are here 3 linear error models with the true intake as a covariate, and the recall or the biomarker or the questionnaire as outcome. And the last method in this part was the linear regression analysis. There we considered the following linear error model. The urinary sugar intake was the outcome, and the 24-hour dietary recall reported sugar intake was one of further covariates. In the second part of the analysis, we assumed the following assumptions. In the naive method, we did not assume a specific measurement error structure, but if individual means, if repeated measurements were available, we calculated individual means. And we did that for the 24-hour dietary recall reported sodium-potassium ratio and for the corresponding biomarker. In the classical regression calibration approach, we fit an error model with the urinary sodium-potassium ratio as outcome, and again, the recall as one of further covariates. And then we were able to estimate the expected value of the biomarker given the reports and further covariates to predict the biomarker. So that's our regression calibration equation. And finally, our last method, we used the so-called NCI method, which is a nonlinear, which assumes a nonlinear mixed effect measurement error model, which accounts for the skewness of the intake distribution, the daily variation, and covariates. And here we consider two different sets of covariates, one with and one without the sodium potassium biomarker as covariate. Furthermore, we assumed that the recalls were unbiased, and then we were able to estimate the usual intake, which we also use for the validation part. Yeah, let me now describe the results. So were we able to validate the intake of total sugar and sugar density reported with the 24-hour dietary recall using the sum of urinary sucrose and fructose. First, here are the results of the correlation analysis, and we found out that there is a correlation of about 0.3 between the urinary sucrose plus fructose and the total sugar and sugar density, and that was true for the same day. And if we considered multiple recalls and estimated the usual intake, that was also true. Regarding the method of triads, we estimated validity coefficients for the 24-hour dietary recall reported sugar intake and sugar density of around 0.8 or 0.7. And again, that was more or less the same when we considered multiple days and estimated the usual intake. In the linear regression analysis, we found out that the log-transformed urinary sugar biomarker was positively associated with the reported intake of total sugar. That was again true for the same day, when you only considered the same day of measurement, and when we considered multiple days of the recall and estimated the usual intake. Here, as expected, the corresponding regression coefficient were much higher for the usual intake because of the reduction of the variance in the exposure. Let me now come to the second part of the results, where we tried to correct the associations between dietary sodium-potassium ratio and blood pressure. First of all, I want to present the results, intermediate results of the fitted error model in the classical regression calibration approach, because it made us very happy, because we found out that the urinary and dietary sodium-potassium ratio were positively associated with each other, and that the corresponding regression coefficient, beta R, was around 1. That was true for the unadjusted and for an adjusted model. So that means that there's no multiplicative error for the sodium-potassium ratio reported with the 24-hour dietary recall. Nevertheless, when we estimated the corrected associations of sodium-potassium ratio and systolic blood pressure, we were not so happy anymore. The reason was the following. When we considered as the exposure the 24-hour dietary recall and applied the different methods, the naive method, the NCI method, and the NCI method considering the sodium-potassium ratio biomarker, we get the following effect estimates. So the effect estimate in the naive method was close to 0, much higher for the NCI method. But then when we considered the biomarker, this effect estimate decreased again. When we considered the biomarker as outcome in a naive approach, we get again an effect estimate of around 0. And that was also the case when we considered the regression calibration approach. The reason for that is that we here, or that we here get the same values, is that the regression calibration approach adds only 1,000 individuals or observations to the analysis. Yeah, all in all, that's a very inconsistent figure. So it seems that not all approaches corrected the associations properly. Yeah. So let me summarize the results. Regarding the validation analysis, I think it supported the relative validity of sugar intake assessed by self-reported 24-hour dietary recalls in children and adolescents. These results were published 2 years ago by us. Regarding the correction of potential associations, we've seen that there are different regression calibration approaches are possible. The advantage of the NCI method is that it reduces the bias due to daily variation, and that the classical regression calibration approach can make use of the largest sample size because it needs only a biomarker or the 24-hour dietary recall available. Nevertheless, the different approaches led to completely different estimates. So caution is needed when interpreting error-corrected associations. And the reasons for that are that we might have differential error or too much differential error in the 24-hour dietary recall, which cannot be corrected using the NCI method. And that we have maybe too much random error in the spot urine biomarker measurements. Yeah, and to overcome this, we need more data. We need combined and repeated 24-hour urine and 24-hour dietary recall data to overcome this. Yeah, thank you very much for your attention. And now I'm open for questions. Thank you.
Thank you, Tim, for a very clear presentation. And I have so far not seen any questions here, so I will start with one.
Okay.
So, just to summarize, what are the big pros or cons with spot urine biomarkers?
Of course, the advantage is, of course, that it's objective, but yeah, the disadvantage is that we have maybe too much random error in it, so that's maybe too difficult or to use it in a regression in a regression calibration approach. Yeah, that's maybe the problem. So my idea would be to have more data and to maybe even calibrate the spot urine biomarker. That would be great.
That's true. Thank you. I will continue with another one here. What food items or food groups would you say are in advantages to measure with the 24-hour recalls?
Sorry, I didn't get the question.
So which food items, specific items or food groups, would you say is the biggest advantage to measure with the 24-hour recalls?
Of course, the problem of the 24-hour dietary recall is that we assess only days, single days, or a small number of days. So if some food items are consumed episodically, for example, the best example is always fish intake. Most people only eat once or twice a week fish. So I would say the bigger the food group, the easier is to handle is in a statistical approach. So, for example, big food groups like food and fruits and vegetables, for example, that would be maybe a better approach. So I would say we can estimate the intake very well if it's consumed on a daily basis.
Yeah, it's more difficult with irregularly eaten foods, of course. Yeah, that's true. I got a new question here. The sodium data in food databases, at least I think it's not very good in the Swedish food database. Could that, sorry, I take it from the beginning. The sodium data in food databases, could that have been a problem when looking at the potassium biomarker?
Of course, if there are already errors in that data, or that makes it even more difficult. Yes, we use the so-called Bundeslebensmittelschlüssel, so the German food composition database. And to be honest, I don't know how good it is really.
Yeah, could be a problem, of course. Okay, Tim, I haven't seen any new questions here. So I think we will thank you for your presentation.
Thank you very much.
And I will introduce the new speaker. And that's Anna-Karin Lindroos, PhD and Risk and Benefit Assessor from the Swedish Food Agency. And she will present their data on nutritional biomarkers in the Swedish National Dietary Survey called Riksmat on Adolescents. So please, Anna-Karin, the floor is yours.
Thank you for inviting me to give this talk. And I will talk about biomarkers in a slightly different angle. As a representative from a government agency, we use biomarkers in a bit different way than in the research on diet and health outcomes. And what I want to talk to you today is about how we can monitor diet and nutrition with biomarkers. And traditionally, we use dietary surveys for many different purposes in the food agency. We want to monitor food consumption and diet in the population. And we can assess risk of nutrient deficiencies in the populations, identify risk groups with poor diets, and assess exposure of contaminants and risk assessments, and use it as a basis for developing dietary advice, and also as a basis for modeling studies where we want to estimate effects of different actions to improve population's diet. And that could be both in nutrition, toxic substances, or environmental sustainability modeling, or health and economy estimations. However, I mean, of course, we are aware that the dietary information we get from dietary assessment are not perfect, and we have underreporting, we have misreporting, but that's the best we have. And I think it's nice to be listening today to all the talks about how we can improve the dietary assessment with biomarkers. So that's for the future, I think we can get better data. But for in the national surveys, we can also use blood and urine samples it provides additional information. And as I'm going to talk today, is about the nutritional status, but we also use the blood and urine samples to assess exposure to contaminants. And there are many challenges when you want to collect biomarkers in a national study, because how do we get the representative groups? Often, especially when we go to, in our studies, we go to the population registries and we want to get a representative population. But it is a problem now that people don't want to take part in studies, and the response is declining. And that's a big problem because we want representative data. And if we add things like blood and urine samples and other measurements, it may be more complicated to take part, and people may be even less likely to want to take part in a study. So that's a huge challenge for us when we want national data. Another problem is, how do we organize the sample collection? Because I mean, we are dependent on many clinics in the country. We cannot. I mean, if we want people from up in the north of Sweden to the south of Sweden, we need to collect the samples in a organized and in the same way. But how do we have those contacts? And when we started to collect blood and urine, we started in the adult survey in 2010-11. And it was only a small sample, but then after having tried different ways, we established a collaboration with environmental and occupational environmental medicine clinics in Sweden. That worked very well. So there are 7 regions in Sweden, and they have helped us to collect blood and urine samples so that we can get samples from all over Sweden. And then it's also a challenge what to analyze. And when we talk about the nutritional status, we want to use markers that we know are well established, that we can follow over time, that we can compare with other studies, and that we know works pretty well. And also for nutrition, it's important to choose markers or compounds to analyze that actually is related to what we think might be a nutritional problem, not just so that because we have to limit how many analytes we can analyze. But also the problem is how do we finance these sample collections and analysis? And when we started the biomonitoring collections, this was very much in the interest of our colleagues at the National Food Agency to analyze analytes that were contaminants. And the Swedish Environmental Protection Agency, they were very interested in finance the analytes, the contaminant analytes. And so the nutritional part was really made possible by collecting data for contaminants. And we were happy with that they were happy, the Environmental Protection Agency were happy to have financed this. And also in the next study, the adolescent study that I will give some examples from, the Swedish civil MSB, what's it? The Swedish civil, no, I lost the word, but it's the contingency agency. They also helped financing the adolescent study because we made it as an exercise. We said that if we can collect blood and urine from adolescents all over Sweden, when it's no crisis, when it's a crisis, we have the methods to do it. So that's how we could get the data, blood and urine collections financed. But also there are ethical issues, and with the new laws of GDPR, it's made even more difficult. And of course, it's very important that we protect the personal information and handle the data in a correct way, but it's also a lot of challenges to find out how to do this in a correct way. And that makes it also very difficult to have open data, because when we start to collect blood and urine, we need to keep the codes of the people who have provided blood and urine. And that makes the data not very, it's always possible to get back to the code and to see who is who. And that's why we have to be very careful with how data is used outside the agency. And now moving over to the Riksmaten adolescent study, which we collect in this way. We actually selected schools all over Sweden, national representative schools. We invited the schools, and one class or two classes from each school were invited to take part. So in the end, we ended up with 3,499 participating in pupils, and about 1/3 of these provided blood and urine samples, and I think, 1,105. And the orange parts shows the municipalities in Sweden that took part in the survey. And in the survey, the subjects were asked to record everything they had for drinks and eat, and they ate in a web-based 24-hour records, 2 different days. I'll show you a bit later. They responded to questionnaires. They wore an accelerometer for 7 days, and height and weight were measured. And this is the Riksmaten Flex, the method that we used. It's a web-based method that is validated, and the questionnaires that are integrated on the front page of the method. And it's 2 days recall, and it's this day 2 in the middle was the school day, where they also recorded what they ate and drank. But this day is not often used in the analysis because it's done differently from day 1 and day 3. And the foods and drinks are connected to the National Food Agency's food composition database. So all pupils in a selected class took place, were invited to take part. It was non-fasting blood and urine. And the staff from the occupational environmental clinics went to the school and collected the blood samples. And the samples temporarily stored at the AMM, the occupational environmental clinics, and then sent to the Swedish Food Agency for a long-term storage before the samples were analyzed. And this is just to show that it's a lot of things that we analyzed in the survey, mostly contaminants, but I will focus today on the nutritional and biomarkers. And ferritin, CRP, and folate were analyzed at the academic hospital in their routine lab. And also, that was also done for the spot urine for sodium and potassium. And we also analyzed 25-hydroxyvitamin D, and that was done in Norway at VITAS, which is a HPLC-MS method, using this method. And iodine in the spot urine was analyzed with an ICP-MS method in Finland. And now I'll just give you some examples. And if you start to look at the iron intake in this left panel, average requirement is what you use, rather than recommended intake, you use average requirement to estimate the population, if the population has enough or report enough of the intake. And what you can see here is that the girls, over 80% of the girls in grade 8 and high school had intakes below average requirement, which is because also girls have a higher recommended intake than boys. And the main sources of the iron in the study came from cereal foods and meat and eggs. Then if you look at the proportion of the plasma ferritin is not really direct. I mean, there's so many other aspects of why you have a low ferritin. It isn't a measure of iron stores, but it's not just diet, it's also physiological aspects. It's about the girls, they lose blood in their menstruations, and also absorption differs between if you have a low stores or not. So there are many different aspects, but what we wanted to know is whether iron, whether the intake influenced or was associated with the plasma ferritin stores. And what we can see here, it's a big difference between the over 80% reported too low intakes, whereas when you look at the actual stores, it's much less. On the other hand, it's a large proportion of the girls in grade 8 and high school that had very low iron stores. The less than 50 milligrams per liter is what WHO has as a reference for low iron stores, which means that we need really to find ways of doing things for these girls but it may not just be diet, but we will do more deeper analysis to see if we can see any associations with diet and these low stores. Folate intake, where is also, it's not as big proportions that have low intakes below average requirements, but there are still a proportion, 25% in the high school, in the girls between 15 and 25, depending on age in these age groups. If you look at folate plasma concentrations, which are, the reference is below 6.8 nanomole per liter, there are, especially in the boys in high school, we see that they have low plasma concentrations, and we don't know what this is. This is because maybe it's the boys in these age groups, they grow very quickly, and maybe they use up their, but then maybe it's a temporary low intake, low concentration level, but this is something we need to look into more deeply as well. Vitamin D intake. In the orange bars to the left is the intake below average requirements. This is boys, and you can see that the majority have intakes below average requirements. If you look at the green bars, it's the concentrations in plasma below 30 nanomoles, which represents deficiency. And that in grade 5 and 8, very few had low concentrations, whereas it increases a bit in grade 2. But on the other hand, below 50 nanomoles, which is insufficient status, it's quite a high proportion in the oldest group, and it increases with age. And if you look at girls, you see a similar picture. And yeah, and this is what we are also looking into this in more depth, and we see that intake to some extent is associated, Byron, with vitamin D status. If you have been on a sunny holiday, we can see associations with those who have many minutes in sedentary time is also associated with the vitamin status. But the biggest difference that we see is that those born outside Sweden had lower plasma concentrations. And the majority of those coming from outside Sweden came from Syria, Iraq, and Middle East, Afghanistan. So that was quite a big proportion, especially in the high school of those. But it's quite a small group, making it very difficult to understand. Diet cannot explain that they had lower concentrations, plasma concentrations, but we haven't got it's about 100 children born outside Sweden, which makes it a bit difficult to go very much deeper with our data, but this is something we are doing at the moment. Iodine, we just have spot urines, and here we just compare with the median value of the population, because it's just spot urines, and we compared with the WHO reference values. They say that a median of 100 to 200 micrograms per liter in spot urine, that's a measure of that status is satisfactory. However, if you want to be pregnant, for women who want to be pregnant, they say that you have to be about 150 micrograms per liter. And as you can see, the concentrations are quite low, close to 100 rather than 150. In Sweden, Sweden salt is fortified with iodine, and we have quite a high fortification compared to other countries. But so as long as you use fortified salt, you will probably get enough iodine. And schools in Sweden use salt that is fortified with iodine, whereas if you buy ready-made foods, the industry may not use iodine salt that is fortified with iodine. So that could be a problem. So it's important to stress the importance of using the iodine, salt with iodine. Sodium, we heard earlier today that it's difficult to measure sodium using the food composition database. The population goal is 6 grams per day, and if we calculate intake from the spot urine on a group level using creatinine as a correction factor, we can see that the intake is around 9 grams per day for boys and 7 for girls. However, as you can see from the calculated intake from the food composition database, the values are actually quite close. I think the problem with food composition databases is that it's difficult to know how much salt people put in their own cooking and how much salt they put on their food, which is not captured it's very difficult to capture when you assess diet. In summary, nutrient intake was in general satisfactory, but a large proportion of participants had values below average requirements for iron and vitamin D. They had a high risk of iron deficiency in the older girls. In general, it was a low risk of vitamin D deficiency, but some groups had high risk of insufficient state, relatively high risk of insufficient status in some groups. Too much salt, iodine status was satisfactory, and we are continuing with in-depth analysis. They are ongoing now, yeah. And with nutritional biomarkers provide additional information to self-reported data, but there are many challenges in the recruitment and sample collection. And if you can combine combine the data collection with markers of contaminants, it's easy to finance. But in the long run, it is difficult to recruit people to studies when you collect blood and urine samples, in addition to dietary assessment, which is also difficult. And the question is whether you can combine it with health examinations. And we have had suggestions to whether it will be possible with the Swedish and Haynes in order to combine health examinations and collect samples for both contaminants and nutritional markers. And I want to thank you, and I want to thank all that have contributed to this survey, and the data I presented today is especially Eva Warensjö-Lemming, Lotta Moreus, and Jessica Petrelius-Siipinen who analyzed data for this. Thank you.
Thank you so much, Anna-Karin. I have some problems with my camera, so I will just, now it seems to be working fine. So thank you so much. So we have time for some short questions, and I got one. Anna-Karin, what is the future plans for collecting urine and blood samples for measuring biomarkers in future Riksmaten studies?
Yes, that's a very good. That's a very good question. We are currently planning to. We are planning a new survey on small kids, and we are planning to include biomarkers in that study. And currently, we are testing the methods in a pilot study.
Okay.
But it is a challenge with finances, how to be able to do it. So we have not a permanent solution for future surveys that it will always be financed these parts. So it's a challenge every time we start a new survey.
So that's why, yeah, you explain that you have to combine it with contaminants. Or yeah, it's easier to get them, yeah.
But it is a problem in general, I think, that the finances, if you want to apply for research money, it needs to be innovative questions and move the research field forward, whereas monitoring is something we need to do for society, but it's not very challenging. I mean, as a research project, it's more important. It's important for us as a nation, but it's not a challenging research projects, which makes it maybe more difficult.
Yeah, that's true. A short last question. So when analyzing the nutrient intake, Was selenium also included? If
No.
so,
No.
no. So yeah, the question was how was the correlation with iodine, but then yeah, it wasn't included.
No.
Okay, thank you. Yes, thank you so much for the presentations, and we will have a short break. Now we're a little bit late in the schedule, so it will only be 5 minutes. So we will start again 5 minutes to 11. Thank you.
All right, welcome back from the break. My name is Suzanne, and I am honored to introduce the last speaker of this webinar. Susanna Larsson is an associate professor at Uppsala University, and she will tell us about genetics as objective markers of dietary exposure. Susanna, the floor is yours.
Thank you. Can you see my presentation?
Yes.
Okay, so yes, thank you very much. I will talk about Mendelian randomization, MR, as a tool for assessing causality of nutrition disease associations. So MR uses genetic variation as a natural experiment to investigate causal associations between potential risk factors and diseases. Here is an example showing the similarities between an MR study and a randomized controlled trial, assessing the association between increased calcium levels and risk of myocardial infarction. So a genetic variant in the calcium sensing receptor is strongly associated with circulating calcium levels and can be used as a genetic instrument to proxy calcium levels. So individuals with the TT genotype of this variant will have higher calcium levels than those with the GG genotype. Because genetic variants are randomly allocated at conception, those with the TT genotype will not differ from those with other genotype except for higher calcium levels. So this corresponds to a random assignment of individuals to calcium supplements and placebo in a randomized trial. The validity of findings from an MR study depends on 3 main assumptions. First, the genetic variant should be strongly associated with exposure. Secondly, the variants should not be associated with any confounders of the exposure outcome relationship. And finally, the genetic variant should be associated with the outcome through the exposure and not through any other causal pathway. Genetic variance has been identified for most essential vitamins, minerals, and fatty acids. However, the number of genetic variants are quite few, ranging generally from about 1 to 15. And the genetic variants, some of the genetic variants are in relevant genes. For example, genetic variants that predict vitamin B levels are in genes involved in the metabolism of folate and homocysteine. And low levels of certain B vitamins increases the levels of homocysteine, which may be a risk factor for cardiovascular disease. So we use genetic variants in these genes to assess the association between circulating B vitamins and homocysteine and risk of coronary artery disease and stroke. And we found no association between genetically predicted B vitamin levels and risk of coronary artery disease, but found that higher levels of folate, vitamin B6, and homocysteine were associated with a certain subtype of ischemic stroke, the small vessel stroke, which is related to endothelial dysfunction. Many MR studies have assessed association between vitamin D levels and different diseases. Most of these studies have used between 4 and 7 genetic variants that are located in genes
relevant for vitamin D synthesis, transport, or metabolism. And results from these studies have shown that increased vitamin D levels within the normal range is unlikely causally associated with bone mineral density and the risk of fractures, cancer, and cardiovascular disease. However, there is some evidence that higher vitamin D levels might decrease the risk of Alzheimer's disease and multiple sclerosis. With regard to minerals, we have examined the association between genetically predicted calcium levels and risk of coronary artery disease using genetic variants in the calcium sensing receptor and 5 other genetic variants that are strongly associated with calcium levels. And our results show that increased calcium levels is associated with an increased risk of coronary artery disease. And these findings are consistent with results of some randomized control trials that have shown that calcium supplementation may increase the risk of coronary artery disease. There are also some genetic variants that are associated with alcohol consumption, coffee, and milk, and certain other foods and beverages. For example, genetic variants in alcohol metabolizing genes are associated with alcohol consumption, and variants in genes related to caffeine metabolism are associated with coffee consumption. And the genetic variant near a gene in the lactase gene predicts milk consumption. In a recent genome-wide association study in about 450,000 participants from the UK Biobank, they identified around 800 genetic regions associated with different foods and dietary patterns. And the most heritable dietary factors were milk, butter spread, and alcohol intake, and also a healthful dietary pattern. And this dietary pattern was mainly defined by the type of bread consumed, whole meal versus white bread. And the foods in this pattern were all more or less genetically correlated. The authors conducted an MR study to assess the association between this healthful dietary pattern and risk of coronary artery disease and type 2 diabetes, but found no association. However, this genetically predicted dietary pattern was strongly influenced by education. Alcohol is mainly metabolized by alcohol dehydrogenase and aldehyde dehydrogenase. And individuals that are fast metabolizer of alcohol to acetaldehyde or slow metabolizer of acetaldehyde to acetate tends to consume less alcohol due to discomfort from elevated acetaldehyde levels. So genetic variants in these genes can be used as unbiased proxies to estimate the effect of alcohol consumption on different diseases. So we have conducted a MR study to assess the association between alcohol consumption and different cardiovascular risk factors and cardiovascular outcomes, and found that genetically predicted alcohol consumption was strongly associated with higher blood pressure and higher HDL cholesterol, but lower triglyceride levels. We also found a strong association between genetically predicted alcohol consumption and increased risk of stroke, but we could not confirm the observational findings that alcohol consumption is protective against coronary artery disease. If anything, alcohol consumption was associated with an increased risk. We also found suggestive association with some other outcomes like atrial fibrillation. And the association between genetically predicted alcohol consumption and stroke and coronary artery disease was also assessed in a cohort of Chinese men. And this study confirmed also an association between higher alcohol consumption and increased risk of stroke, but found no association with coronary artery disease. The World Cancer Research Fund has concluded, based on observational studies, that consumption of dairy products may decrease the risk of colorectal cancer. We used a genetic variant near the lactase gene and found that higher predicted milk consumption was associated indeed with a lower risk of colorectal cancer, confirming the observational findings. We found no association between this genetic variant, or at least no consistent association between this variant and other major cancers. There are several major challenges of MR studies, in particular of nutritional factors. For example, intake of foods, beverages, and nutrients are strongly interrelated. For example, the lactase persistence is associated with milk consumption, but higher milk consumption will likely lead to lower intake of other foods to compensate for the energy intake. And genetically predicted coffee consumption is not only associated with coffee, but also with standard black tea consumption. And therefore it's difficult to disentangle the independent effect of specific foods and beverages on disease risk using the MR design. And genetic variants associated with food and nutrient intake are commonly associated with genetic variants associated with educational level, body mass index, and other potential confounders. And this will violate the MR assumptions. And there are also a quite limited number of genetic variants that have been identified for most circulating nutrients. So the conclusion or the key points here are that MR studies can be used to improve causal inference in nutritional epidemiology by reducing confounding, reverse causality, and misclassification of exposure. And this MR design has been increasingly used in recent years to assess potential causal associations of nutritional factors, such as alcohol, coffee consumption, and milk consumption, and different circulating nutrients and metabolites. And MR studies have confirmed some, but not all, nutrition disease associations that have been recognized by traditional observational studies. And while the number of nutritional factors with appropriate genetic instruments has increased during the last years due to increased number of GEOA studies, they are still lacking reliable instrumental variables for many nutritional factors, and in particular for intake of foods and beverages and different nutrients. And thank you for listening. That was all I had to say. Any questions?
Thank you for the very interesting presentation. Yes, we have a few questions for you. Thanks for this interesting talk. Are the lactase-related SNPs still a good instrument to use for milk consumption, considering the large number of lactose-free milk products available?
That's a good question. Probably not, because it's mainly related to milk that contains lactose.
Yes. These ADH and ALDH may be biased because they are directly involved in alcohol metabolism. Are they cause or effect?
Oh, that's a good question. I don't know really.
All right. We have another question here. The MR design is very elegant. However, when reading MR studies, my experience is that the SNPs explain only a few % of the variation of an exposure, for example, for calcium, within a population. And the exposure itself might also only explain a few % of the outcome, for example, for CVD or cancer. meaning that very large number of participants are needed in the studies. Therefore, non-individual data as UK Biobank is often used. How, if in any way, would you say that that affects how to interpret the results of MRs?
The main limitations that the genetic variance only explains more proportion of the variation is that you need very large data set for the outcome. And so it's not that it will lead to biased results if the genetic variance explains only small variations. So, and also it's important to use genetic variants that have been identified in one population, and then the outcome should be from a totally different population to avoid bias in the same direction as the observational association.
Yeah, great. We have another question here. Is MR the best way to explore the causality between diet and diseases? What are other methods?
Oh, that's a tricky one. It can be used as a complement. I would say that we need different types of methods to reach a more firm conclusion regarding association between nutrition and outcomes. So if we have support from both MR studies and other types of observational studies and the randomized trial, then we are quite convinced that association is probably causal.
Great. Yes. In the MR study on alcohol, refuting the observational findings of CVD, is there a dose information included in the finding you showed for MI or stroke?
Yes, in the Chinese study, they could look at the dose-response relationship between genetically predicted alcohol consumption and risk of stroke. So it was quite a nice dose-response relationship in that cohort, because they used individual level data so they could do this type of dose-response analysis.
Okay, and what research would you like to see regarding genetic biomarkers of diet going forward?
I think we need, first of all, we need more large GWAS studies to identify more genetic variants for each nutritional factors, and also to identify genetic variants for factors that we have no genetic variants yet.
Yes. Thank you. I think that was our last question for you. So next on the agenda, we have the panel discussion. So I'd like to ask all speakers to turn on their video and unmute yourselves. And with that, I give the word to Emily and Stina.
Yes, hello. We will try to manage to create some sort of panel discussion here. Just want to make sure who from all the speakers are here, but it seems like most. And the plan is that we will try to go through a bit of the questions that we have missed during the 2 days. And if you have some additional questions, you can also ask them in the Q&A now. But then we also have prepared some more like broader, deeper, visionary questions that we want to hear the different experts here opinions on. So we will make sure that we have time for those more complex questions. So yeah, me and Emily, we are the hosts here. So I think that we will ask out the questions, and if you as a panelist feel like if it's not directed to a particular person, if you feel like you would like to answer the question, you can raise your hand in the, or is that possible even for us who are panelists? Maybe not.
You can just raise your hand, maybe.
Or you can raise your hand physically, or just start talking if it's that works. So among the questions that we have received during the days and we have not had the time to answer, maybe we could direct a question to Lars Dragstedt. Maybe you want to discuss between plasma, feces, urine, which is the most promising for dietary biomarker discovery, and the advantages and disadvantages of the different biological sample sites.
Yeah, I would say that in general, we try to look very much into urine because you have a sample that is accumulated over a defined time period. That means you have the excretion for a certain time period, and then you accumulate everything that is excreted within that time period. Whereas blood is a spot sample, so you get just a momentary picture of what you're doing. Comparing these two, I would have expected urine to be much better than plasma samples. But I would say in my own experience, I cannot say so. There are actually a lot of good markers in plasma as well. So we could have gone for that mainly. And also you have all the lipid markers. You have the lipid phase in plasma that you do not have in urine. So that gives an additional possibility there. For the fecal samples, it's much more difficult because we have no measure of what a fecal sample represents in terms of time. Some people have a very frequent and others very infrequent defecation rate. So that means we don't know exactly what they mean. So I think the fecal samples still have to be developed as a tool for biomarker research. But of course, they contain all the waste, everything we could not absorb. So there is a potential there for additional markers, different kinds of markers.
Yes, thank you. Does anyone else have a comment on this? Your choice of biological sample?
Tina, do you see everyone? Or?
No.
No, exactly. So we don't see your hands.
Can I raise my hands?
Yeah, you can talk.
Oh, perfect. I think the one type of samples we sort of ignore too much are hair, nails, possibly teeth. I know teeth are sort of a little bit exotic, but if you think about the formation of teeth, they form very early in life at a time when we can't really get any dietary information with any reliability. And I know in archaeology they're used quite commonly. And I've got a collection of teeth. I know this sounds awful, but I've got a collection of teeth and I haven't managed to analyze them because it's sort of a side project. But I think hair is used in toxicology, teeth are used in archaeology, and sort of something. It's definitely not a mainstream nutrition approach, but I think it's something we overlook maybe a little bit too much. It's sort of the thing you could do when you have sort of spare time, sounds the wrong way, but sort of the kind of lab experiment you do sort of to relax and do something else from the usual. It's sort of a really exciting source, which I think we need to look into more, especially long-term. With hair, we have very, very long-term intake. We have months if you have actually long hair. Nails and things like that, and they're easy to collect, and you can ship them, you can store them. So I think it's something we probably need to think about more a bit, even though it sounds a bit creepy.
Yeah, but I also assume that if we would start analyzing teeth and nails, we wouldn't need to develop ways to measure those.
Yeah.
More. Yeah.
Oh yes, we need methods. Yeah, we're very, very at the beginning, but
yeah, very interesting. So any?
I think Lars wants to say something.
Yeah, go ahead.
We have worked with both actually, with the teeth in terms of figuring out from skeletons when they started eating meat more regularly and things like that. But the amount of calcium really makes it difficult to analyze. So we didn't finalize a good method for it. For hair, not everyone has a lot of hair. So it can be difficult to collect from some people. But otherwise, I think it's a very interesting specimen, and we are working much on it right now, and it looks very promising.
Yes, I'm trying to find another question that we have missed today that could be useful. Utto is not here, right? No. Okay. But maybe we could ask Tim, you have a question here. Different calibration methods with different results. How to decide which method to use? What are the assumptions?
Yeah, that's a good question. Yeah, I mean the main outcome of this part of the analysis is that we get totally different estimates, and we don't know which one is correct. The only thing we know is that we have different kinds of measurement error in the data, and the different methods only correct partly correct for it. So it's not clear. So yeah, the conclusion is that we really need more data on this. So we need repeated 24-hour urine and 24-hour dietary recalls. To find better regression calibration equations. Yeah.
Let me see. Is there anything?
Maybe we can ask the question if anyone, maybe Lorraine, have a link to the more flexible approach to biomarker that you mentioned. You have the link.
Yeah, well, I think Lars headed up that work, so he's better able to speak to it about than I am. So we can circulate. There's a paper about it. We can circulate that to you at the end.
Very good.
I could send it out now. I actually Googled it to find it, so share it.
It's open access.
Good. So I think it should be this one. No, sorry, I sent it to only the ones on the panel. Okay, let's see. Should we take some of the more deeper visionary questions, Emily? It's time.
Yeah, I think so. Maybe we can start with those of you that have been involved in this, like bringing out new biomarkers. I want to know what was the biggest challenges? Was it harder than you thought from the beginning? Should we start with the football project, or who wants to start? Lars? Yes.
I can say something if I'm talking too much, I think. Yeah, the biggest challenge in untargeted metabolomics is the identification. I mean, that's what takes the time. I mean, you have your students there and they have no hair left when they're done because it's all pulled out of their head because it can be so difficult to do. But also very rewarding when you manage and you find this new molecule that no one has described before. But that's the time-consuming part.
Yeah, and I completely concur with Lars. I highlighted it in my talk as well. Identification is a real challenge, but I think it's also a bottleneck in the whole field.
But like if we then think, because a lot of the studies used to identify biomarkers, then it's sort of based on an acute intake, and you look at the postprandial as a first step. But how often do those biomarkers that show a like postprandial curve actually turn out to be good markers of intake when you take a fasting sample? or how challenging is that? Or is that always the case that postprandial levels, they are also good markers as in fasting samples of more habitual intake? I don't know who maybe I'm also addressing this to Lorraine, or who has.
Yeah, I mean, I'm sure Lars has experience in this as well. I mean, I guess if you do take your postprandial samples and you've looked at them at a 24-hour time point and again at a 48-hour time point, post the initial consumption of the food, and you still see some elevations, we have found that those ones work quite well when we try to then use them in fasting samples. They all don't work, and we wouldn't expect them to all work, but it's quite a good indication of what could, at least it guides you in the right direction, is our feeling from the work.
I showed a slide where the relationship between half-life and sampling frequency, I tried to illustrate this. So of course, something with a very short half-life might not work the next morning. On the other hand, Lorraine actually showed some interesting results showing that even the second void contains molecules that I would have expected to be excreted because they were past several half-lives. So there seem to be also deep compartments that we don't really understand yet, and that might actually lead to some possibility of catching things that have been, end up deeper in these compartments and then are excreted later on.
Does anyone have a follow-up comment on this? Yes, Ginta.
I think one of the big problems we have with many compounds, so I'm looking more at individual compounds, not large patterns, but I assume that the problem will be the same, is we know for many compounds very, very little about their pharmacokinetics, their half-life, and also how different types of diet affect their absorption. And there's a huge data gap, and it's sort of slowly being filled, but it's the one thing. The sugar biomarker is one of these examples. We don't know much about the pharmacokinetics of sugars, and we don't know much about pharmacokinetics of a lot of compounds. And then we add the microbiome, we add diet interactions, and it becomes really, really complex. And I think it's sort of one of the gaps, which I don't know whether it's a gap which is a nice to have or it's essential. I think for the more detailed we want to get with understanding diet, the more it goes towards essential. But it's sort of one of the big issues is sort of the lack of pharmacokinetic data. And then of course, what follows on is what metabolites do we measure? How can we measure them? How reliable are they? And what methods we can use? But we risk sort of the going for the perfect solution and ignoring the good one. And that's sort of one of my problems. They sort of tend to go to the extreme and then say it can't work because we can't get it perfect. But it's where I definitely see a gap in these kind of data.
Well, it's a good point, because I think, when do you have a biomarker that is good enough? Lars, you showed very nicely, like going all the steps in the validation. But can you say that this is now we have a good enough biomarker?
Well, I can say that in the paper that has now been linked here, we stress very much that you still have to consider even well-validated biomarker, whether it will fit in a certain study. So maybe you have a slightly different population than the one that was originally it has been validated for. Maybe your sampling scheme is different and so on. So it's always on the experimenter to think carefully about whether it's valid for a certain purpose. also the way you're going to use it, whether that's what it can whether it can actually give you the results that you expect. So I think, I mean, these validation steps, I think they are quite general, and I think they would actually also go beyond intake biomarkers. I think you could use the same 8 or 9 validation criteria also for effect markers or markers of health or susceptibility. But we still need to do some work in order to show that this is actually the case, or whether additional validation points need to be taken into consideration. I don't know if it's answering your question.
So we get some questions. Do you hear me, or should you take it, Stina?
No, we can hear you now. So
you can hear me, great. Because we get some questions here. We can, for example, like, do you think there is a future for smaller labs doing their own metabolomic analysis, or will future cohort study more utilize companies like Metabolone or Nightingale? So this is the question, if we should focus on the big companies or smaller labs.
I think there's always a role for smaller labs. I think we will move to larger companies for high throughput, large scale analysis, but there will always be gaps to look into in smaller labs. If I think recreate everything and redo all the analysis, that's sort of wasted time and effort, because a larger lab is much better than high throughput. But there are always smaller analysis. They're always testing new ideas. Where smaller labs are crucial, and sort of the smaller scale studies or studies where simply it's difficult, pilot studies, that's what the word was I was looking for, where it just might not be feasible to go to a larger lab. I think it's important. I think not recreating, but testing new ideas or trying out new things. That's where a small lab still works quite well.
I think also you have to be very careful for the application you want. Mm-hmm. So while Metabolone have some exogenous metabolites included in their platform, the majority will be related to endogenous metabolites. So you're not going to get the biomarkers of food intake, and they're not going to do the hard grit work in identifying new biomarkers for you. So I think there's a role for both, depending on the application.
And especially if you want to tailor things to what you want to do. If you want to have exotic metabolites or something like this, it's sometimes easier to do it yourself first in your own lab. And analytical technology has become quite easily available, so it's not that difficult or work with someone to do the analysis. I think we shouldn't disencourage people from doing things just because they don't have a large lab.
I completely agree. I mean, you start out and get your experience, and the companies are, as also Lorraine says, I mean, they are not going to do this software. And if you use the companies, then you are only looking at the usual suspects of molecules, nothing novel. So if you want to go into novel areas, I think you can start out in small labs as well. That said, of course, the companies they have very good analysis. I think in many cases, you get more exact values for many things. So if you're interested in the endogenous metabolism, I think, and the endpoints you're interested in, the markers you're interested in are there, then it may be worthwhile if you have the money, that is.
So what do you think the field of nutritional biomarkers should prioritize? What is needed to steer the field forward now? Or is it just going great and just continue?
mean, we just sold the coast of the land, and maybe we stepped on the beach. I mean, we still need to cover. I mean, there's so much validation. There's so many areas we haven't seen yet. I mean, we have a certain level of sensitivity of our analysis. Maybe we can measure a few thousand compounds in one go if you have very good equipment and so on. However, there are 100,000 out there. So the amount of additional information further down, and all the work with combined markers, which is, I mean, there's not going to be a simple marker for everything. And the questions we are going to ask are going to be more and more detailed. So we will need more and more resolution and new smart ways of doing things. So I see this field expanding and developing for the next 10 years at least.
Yes, and maybe to pick up on that, about combining biomarkers to capture a pattern or a specific food with multiple biomarkers. How do you see the future of that, if anyone has experience?
I think the literature now, it really shows that that's probably what's going to happen, is that you're going to have multiple biomarkers for a specific food. That comes with complications. So as Lars indicated as well, that there's loads of work that needs to be done to see how you combine them, what's the best combination of them. We need new statistical methods so that we can combine them correctly, so that if we are interested in getting continuous intake out of them, as opposed to getting just categorical intakes. So there's a huge area of work to be done there, both from a modeling perspective, but also from thinking about how to combine them. How do you decide that a biomarker doesn't end up in the panel, and et cetera, et cetera. So a lot of work to be done, but I think it is where the excitement lies at the moment, is in that multiple biomarkers.
I agree, and also, I mean, you can always make a biomarker by multivariate statistics. You will get like 30 or 50 compounds that are part of the model, but that's impractical. When you want to go to a target method afterwards, you need a parsimonious model. So you should find the 3 or 5 compounds that are covering well your question, rather than taking everything. And sometimes actually, when you go down from like 20 to 5, you get better prediction. So the current multivariate models, although they should be optimizing your set, they're not good at that. And I also think part of that might be because there is a lot of redundancy in untargeted metabolomes. So you have several markers from the same compound, and that affects the mathematics in the multivariate statistics, or behind the multivariate statistics. So I think we need actually to work closely together with statisticians and others to develop better methods to crystallize out the parsimonious combinations of biomarkers. I don't think anyone has really done that yet. We have tried to work a bit, and a lot of people in this area or in the statistics are really interested in this new field, but I haven't seen the big project focusing on this yet. And I haven't managed to get money myself. I'm probably not good enough at explaining why this is important.
But maybe we can then follow up on that. So if we want to improve prediction, because I think you rarely see that you maybe weigh in other lifestyle factors like smoking or physical activity, and whether those factors are affecting how the biomarker relates to intake. The microbiota also too, should such factors be more included in the when we bring new biomarkers forward, and validating them in the prediction? or do we want to find biomarkers that are, they work either way, no matter if you're a smoker, if you're physical activity, or.
I think we need very robust biomarkers that should not be affected too much. I mean, also, people have different genetics, as we also heard, and the interaction of biomarkers and genetic markers is really interesting, I think. And on top of that, we have, the microbiota affects a lot of these markers, and this will differ between people. So we actually want the most, I often say that the ideal marker is one that is comes directly from food, is not metabolized by us, and then circulates and is excreted, because then it's very neutral. And that's back to your previous question, whether we have these concentration markers and so on and so forth, because then, of course, you have a marker that is really smooth. But that's not real life. Most compounds are actually metabolized, and we have to take this into consideration. And maybe, sometimes we use combined biomarkers to overcome this problem. So if people have if we have several metabolized compounds, then some people will have some metabolized, others will have other metabolites. So you make a combined markers where you say you must have A and B and C, or you must have 3 out of 5, for instance. So you set up several markers that would be relevant, but you know that not everyone has all 5. So you say 3 out of 5, then you say that this is qualitatively showing the intake. We did that for doping, I think, with blood doping in a paper we recently made. And we could see that some of the compounds from that were found in the blood there were different between different subjects. So by taking, I think, 2 or 3 out of 5, we could show that blood doping had been taking place up to 3 days after.
We're soon running out of time, but think about this with combining. So if you are starting a new study now, should you think about, should we just use the biomarkers, or is there a use for dietary assessment methods? Or maybe this is something you have already answered, but I was thinking, you also mentioned that you should collect it like urine once a day for several days. That was more useful than just once. Is that something we should think about? Or how should I think if I start a new study now? Should I collect urine, blood, or nails, hair? What's the future?
The ultimate cohort baseline sampling, how would it look if you could dream?
I can give an idea. I already said it in my presentation, that I think you should have preferably spread over time, like 10 spot urine samples if you want to go for urine. For blood, I think the dried spots are developing very much. I think you could get on with that. And then hair sampling is a very good idea. So get 10 to 50 milligrams of hair from your subjects. And I think that will be very good. But no one can answer this question at this time, because we are, as I said, we just set our foot on the beach, this new land.
Stina, do we have one more question, or?
I have one.
You have one more question.
Yeah, for Susanna, I think this technology is, Mendelian randomization is really, really interesting. And I wonder if you have, so far you combined it with questionnaires, if I understand it right, but not with biomarkers of concentration, or did I get that wrong?
No,
because
actually,
there is a potential to figure out what's going on, and also to figure out a lot of confounding in observational studies will be kind of cached and found because things interact and correlate that we did not think.
In fact, most of the MR studies today have used biomarkers data, for example, circulating levels of calcium or vitamins. So I think it's more reliable than using intake, because intake of different foods are so much correlated with, like education, BMI, and other things. So if we'll identify genetic variants associated with intake of foods, it's much more complicated to use them as unbiased proxies for diet. So I think at the moment the best thing is to go for the levels in the blood, like biomarkers.
Okay, thank you.
And could I follow that up again? It's a question for Susanna. So you've used one biomarker. Have you ever tried using multiple biomarkers or a biomarker signature?
No, not yet, because most of the MR studies today have been based on the two-sample MR design, where you have identified the genetic variants in one cohort, and then you use another cohort to get the genetic variants for the outcomes. So it's more, I think maybe in the future, if you have a very large data set and you have both the information about the biomarker and the outcome in the same cohort and the same data set, then it can be more, you can do more type of analysis, looking at the combination of different biomarkers and so on, and also look at those response relationships.
Yes, thank you. Do we have something final, or it's time to move on?
Maybe it's time to move on. I really want to thank all the speakers for very interesting talks, and thank the moderators for helping out to make a great event, and also Peter Brandén for the technical support. And they, of course, organizers NEON and KVA and EpiHealth. And I really hope to see you in any meeting in the future. We have NEON meetings every year, so hopefully we can see each other next time, or other conferences around. So with that, I thank all the participants, of course,